Okay, hello everyone. Good morning, good afternoon, good day, wherever you are. It's our pleasure together with Sebastian and myself from TU Delft to host this webinar this week again, 17th November. Today it is 4 p.m. European Central Time. Today we have the pleasure and honor to host our colleague Anitha Andiappan from RAG Austria in Austria. Anita studied chemical engineering at the National University of Singapore and ETH Zurich. She worked as a research assistant on heterogeneous catalysis of methane at ETH Zurich. In 2010, she started working with Warnley Parsons as a process engineer in the hydrocarbons team, tackling various downstream and upstream projects. She then completed her master's in petroleum engineering, specifically reservoir engineering, at the Montan University of Leoben in Austria. Anita joined RAG Austria AG in 2014 as a reservoir engineer in the subsurface team. Her work includes the management of gas reservoirs in Upper Austria, as well as developing and managing underground gas storage sites. Furthermore, she engages in renewable energy projects with her subsurface expertise, such as hydrogen storage in natural gas reservoirs. In addition, she is also a visiting lecturer at the Montan University of Leoben. It's a pleasure and honor to host you, Anita, this week. Actually, I should say this month because we are now running it on monthly basis,
Ah,
and we are all very much looking forward to hearing your lecture. To the audience, please note Anita's lecture would last for about 30 minutes or a bit shorter, and then we will have the questions and discussions. Like always, please do chat your question in the chat box, text them there, and then we will highlight them and discuss your question after the lecture. With, without any further ado, Anita, we are all looking forward to listening and attending your lecture. Please start.
yeah. Thanks for a very kind introduction, Hadi, and thanks for having me here today. I'll start with my presentation. Um, yeah, just mm, so that I
Yes,
can.
we see it
Ah,
pretty
you see.
well.
Okay, good.
Yes,
Okay,
yes.
okay. So yeah. Once again, hello from my side, and today I'll be talking about the hydrogen storage in depleted gas reservoirs, as an our experience from a field scale pilot project in depleted gas fields. And before I start, I'll just give a short overview of who we are, as in who is RAK Austria AG. Some of you may know, some of you may not know. We are a leading underground gas storage operator of a storage volume of about 66 terawatt hours and an unloading capacity of 30 gigawatts with 10 storage facilities. And we are also strongly very active in the development of innovative energy solution via renewable energies using our existing assets. And yeah, and I will walk you through the agenda planned for today. So, the background of why we need hydrogen storage, what do we know till now, what would we like to know, and our strategy on tackling the some of the very many open questions. Yeah, and here I would like to bring your attention to the electricity supply and demand in from 2030 onwards in Austria. So it's basically a residual forecast scenario for Austria. On the x-axis, you see the months, and on the y-axis, you see the daily time. And the red portion here, in autumn, spring, and summer, there's a surplus of electricity of up to 12,000 megawatts. And the shortage is depicted in blue color, which then increases in the winter months, and especially in February of up to minus 8,000 megawatts. And this calls for the need of seasonal storage. And where does this energy come from? At the moment, most of it comes from natural gas. And however, for sustainable energy future, I believe it should come from renewable sources. And here, how does the potential of renewable energy look like in Europe? There's a lot of potential for renewable energies in Europe. Here you see on the left, you see a map showing the potential of solar energy in Europe. As you can see, and one would expect, you have more potential in the southern areas depicted in red color. And the same applies to the potential of wind energy in Europe. Here, the legend or the color is the other way around. So the cooler colors depict reflects higher potential. And on one hand, we see that there are seasonal differences in the demand and supply, as I showed in the previous slide. And now in this slide, we see that there are also additionally regional differences in the potential of renewable energy. So one solution would be to produce hydrogen where sources of renewable energies are available and transport it to where it's needed. Potentially, the existing gas grid here that I've depicted or laid over the both wind and solar energy map, the existing gas grid would allow the transport of hydrogen across the continent. However, we are unable to produce hydrogen via renewable energies on demand, nor store large amounts in order to serve the seasonal demand. And that's where we come in with our storage know how. And the idea is to store energy in the form of hydrogen in existing gas reservoirs and retrieve this energy on demand. Today, I'll be talking about mainly on hydrogen storage and therefore specifically looking at the underground sun storage project and sun storage 2030 project. So the underground sun storage project was the first project associated with hydrogen storage where we stored of up to 10% of hydrogen, and it completed in 2017. The follow-up project to this in terms of hydrogen storage was the underground sun storage 2030 project that has commenced March this year, that looks at pure hydrogen storage. In this slide, I would like to give or share the projects that RAG is involved in or was involved in. So the first two projects that I was talking about, sun storage, is the one that I explained previously. And on the other chunk of it, we also do the underground sun conversion. Many of you may have heard it already. And that looks at cre- uh, getting or creating green methane. And we are also acting as an advisor in the hydrogen storage in European subsurface, the HyStories project, and an active member in the hydrogen under HyUspray project. So now I would like to walk you through the steps that we have defined for us on how to store hydrogen in our existing reservoirs. So what is the crux of storing hydrogen? So the first of all, from walk you through reservoir selection, reservoir monitoring, so on and so forth. And the first one is the reservoir selection. So it's extreme, utmost important to know to pick a suitable reservoir and what is a suitable reservoir. So in the first project, we defined that we want a small and isolated reservoir so that we know that whatever we put in, we can get it out. And this was then picked to be the Layan field. And also, why this field? It was small, isolated, good permeabilities of 600 to 1000 millidarcies, and good porosities, and we had a good infrastructure, gas infrastructure around it. In this project, we successfully injected, we stored of up to 1.22 millions of natural gas with 90% natural gas with 10% mixture of hydrogen to a final reservoir pressure of 78 bar A. And in the underground sun storage 2030 project, we picked another reservoir that has similar features such as well isolated, good permeabilities, porosities, and additionally, it also was wanted one more criteria, which is that this well reservoir is able to store the hydrogen produced from a 2 megawatt electrolysis unit at a rate of 400 to 600 norm cubic meters per hour. This project, as I mentioned earlier, has just started in March this year, and we will start with the hydrogen storage also actively from next year March. So at the moment, we are all getting all our surface facilities built. And I come to the second point. So now we've picked the reservoir, we know where we want to store, and how do I do the reservoir monitoring? What are the important parts that I should monitor. In the underground sun storage project, we had continuous downhole pressure and temperature gauges installed, as well as we also had flow meters with gas chromatographs, so to always see that what are the gas compositions that went in, and also more important, what also came out. From the downhole pressures, it was important for me to be able to conduct, as a reservoir engineer, a pressure transient analysis during the entire storage period, or during this underground sun storage phase, and also to compare it with the early life. And here I show there's a table here that I have put together. How does how does the permeability look like from the early life onwards through the pre-field um, pre-field test, and also during the injection and withdrawal cycles. So what we notice here is that we see that the permeability has increased, or as you can see after the field test or the injection. And this suggests that the 1.22 millions of norm cubic meters of natural gas with 10% volume percent of hydrogen that we injected into the reservoir um, swept away the water present from the early life of the well around the wellbore to the deep areas of the reservoir, hence improving the wellbore performance, indicated by the doubling effect of the permeability. This is a phenomenon that also noticed in storage operations, where the well performance improves through cycles of injection and withdrawal. And then here, the last column here, you see I've also some the skin, and it is very common that the skin in an early life, especially when the well is freshly drilled, you have a lot of manipulation through drilling fluid, drilling mud, that causes that you have a shows a high skin, or interpretation of high skin, which then stabilizes usually. And in this case, it also stabilizes to about -2. And with that, we said that the quality of the wellbore region improved due to storage operation through this doubling effect. Then the next monitoring that we had was the temperature, and the temperature monitoring gives me a first indication if anything majorly is not geochemically is not okay, and this would be the first check. And here you see that I've plotted in various colors so that it's easier to have a look. On the brown is the how you guys hear me? Yeah. Yeah. Um,
Yeah,
here,
yes, very much, very well. Yes.
yeah, okay. I just thought. And you see that in brown is plotted, shows the temperature before the underground sun storage project. And then after that, in green, through the injection cycle, stationary, and so on. So I just bring you through. So during the injection cycle, we noticed that roughly it stays about 39 and a half, 39. And during the injection phase, of course, when I bring a cooler gas, it cools down a little bit, and therefore I have a drop in temperature. And then after that, I have a stationary phase where my temperature is able to stabilize again. And during the withdrawal cycle, that my temperature increases because I'm producing warm gas, which then again stabilizes. With that, we say that there seems to be no apparent geochemical changes. In the underground sun storage project that we are just started, the field test has not begun yet. And here, the measurements that we are going to have similarly are the downhole pressure and temperature gauges, so that I can have the permeability checks for pressure transient analysis, and also temperature monitoring. Additionally, flow meters with gas chromatograph, so I know what is going in and especially what is coming out from my storage. This would be very interesting if to see how many percent of hydrogen will I be able to retrieve. And then water sample analysis from before the project start, and to compare it with during and after, to see if anything changes in the microbiome consortia. Then I come to the other topic that is interesting, that I very slightly touched before. It's the geochemistry. So, how does the chemical integrity look like in the reservoir? So, when I say reservoir, yeah, on one side, on one hand, the reservoir rock, and on the other hand, the cap rock. So, what do we know to date is that in terms of reservoir rock integrity, We have tested of up with in laboratories with up to 75% of hydrogen, wet hydrogen. And here on the right, you see the thin sections from one of our core from a representative field of the reservoir rock. And these shows the thin sections of before and after exposure to 75% of wet hydrogen. And what did we notice? That there was no reaction seams, no indication of dissolved grains in any of the thin sections, suggesting that hydrogen storage in wet conditions did not alter the reservoir rock. And in terms of field tests, we conducted with up to 10% of hydrogen mixture, and the behavior, what we noticed was it behaved as expected in a standard storage operation. And in terms of caprock integrity, we tested in laboratories with up to 100% with 100% of dry hydrogen, um, two plugs of caprocks that are in the molasse basin. And what do we notice is on the when we tested with methane and and hydrogen, the permeabilities remain in the same order of magnitude, about -18 to -19. Sorry, this is in German. The rightmost column shows hydrogen and the middle one shows methane. And with that, it suggests that there seems to be no alteration to the caprock tightness. However, we still have some open questions left. We would like to know, how does the exposure to 100% of wet hydrogen in wet would affect the reservoir rocks. For this, we have experiments at the moment in a laboratory setting with, with DBI in Germany. And we also, on the other hand, another remaining blank spot is, how does the caprock mineral behave when exposed to wet hydrogen? So basically, when there are hydrogen ions. And for this, we know that the shale in the molasse basin has some amount of iron bearing minerals, and so we'd like to know, how does this potentially react with hydrogen. And for this, we have laboratories experiments planned out in a laboratory setting in Montaigne University of Leoben. Then I come to the next part of the other topic that we would like to know more, is the flow in porous media. How does the hydrogen move and mix in the reservoir? Um, and what do we know till now from the previous project is that we did a hydrogen balancing. So we brought in of about slightly over 100,000 norm cubic meters of hydrogen, and we retrieved slightly under 100,000. So about 80% of the hydrogen injected was retrieved. So then our question was, what happened to the remaining 20% of the hydrogen? Diffusion, dissolution, conversion, yes. And so then we looked at the physical processes. Firstly, dissolution of hydrogen. So in the solubility of hydrogen was simulated in a freeware called FRIXY software, and which was calibrated based on experimental data from literature. And here we was noticed that the solubility of hydrogen was way less than that of methane, and these results are comparable to other projects in the European side, like from REACT and H2 REACT and High Store POR. And then we also have the with the other part of it is, we tested with increasing salinity. We also noticed that the solubility of hydrogen decreases. So then we thought, okay, that is can't be the main effect. Then we looked at diffusion. And in terms of diffusion, I've specifically mentioned here gas to gas, because in terms of gas to water phase, the dissolution effects would overwhelm the gas water diffusion. And for this, we had laboratory experiments conducted in Montaigne University in Leoben, and you can see the reactor setup here. So it's basically two sandbag columns that we had. On one, it was filled with hydrogen, and on the other was filled with methane. And then it was conducted at 4 bars, and it was so we saw waited till the time, so the how long it took for the hydrogen to meet the methane side. And it took about 4 days for the first molecules of hydrogen to meet the come on the methane side. And calculated for a total mixing only by diffusion, it would be calculated, extrapolated about, it would take about a year. And considering the heterogeneity in the reservoir plus water saturations in the reservoir, this would cause or bring only minimal effects. However, in the field test in underground sun conversion, where we have two wells that are not so well connected, we notice a fast breakthrough of hydrogen when the other well was drilled. And so our question was, why do we have a fast breakthrough of hydrogen in the field test? Is this caused by dispersion, perhaps? And because dispersion tends to occur more in the turbulent flow in the reservoir, and dispersion coefficients are known from literature to be much higher than that of diffusion coefficients. And for this, we have experiments planned out in a laboratory setting to look at this effect. And then I come to the next part, which is the last part, which is the potential of H2S hydrogen, potential of H2S generation, sorry. And as we all know, hydrogen sulfide, H2S, is a colorless gas, addressed as a hazardous gas, addressed as a hazardous gas in the by the European Commission, and hence there are EU regulations on H2S emission standards. In the first project of H2S, we noticed that we do have minimal amounts of H2S production below 5 ppm. However, the open question that remains for us, or we would like to know, is how does the H2S development look like when we have 100% of pure hydrogen storage? And here on the right, you see the metagenome of the bacteria, microorganisms of the water from Rubensdorf, which is in the Underground Sun Storage 2030 project. And here we have a small portion I show here in yellow, which is the Liene bacteria, that is 13%, and some literature suggests that maybe this bacteria could act as a proxy for possible H2S generation via biological pathways. And for that, we have laboratory experiments planned out mimicking the in situ conditions and monitoring how the microbial consortium changes with our partner EVA tool, where we would measure how the anion, cation, DNA sequencing, so on and so forth. And yeah, I think I'm back. Yeah. With that, I come to my summary slide, that what are the findings that we know till now, that there seems to be no negative effects on reservoir integrity. The cap rock remains intact with dry hydrogen, and the experiments show that the dissolution and diffusion are minor contributors for flow effects. And the open questions that we would like to still know would be, how does the cap rock behavior react when exposed to wet hydrogen? What are the major contributors for flow effects? And also this project versus laboratory results analysis. And with this open questions answered, we believe that we will be one step closer to having renewable energies as a reliable source of energy, and therefore a more independent energy system. Thank you.
Thank you very much, Anita. That was an excellent talk. Plenty questions. I actually am accompanied by my colleague Susanna Hanks here. We are actually attending the International Energy Agency gathering on underground hydrogen storage. So, Sebastian, another colleague of us is now here. So, Sebastian stays in Netherlands. We are in Brussels, and now you're in Austria. Thanks to the technology, we're all connected. And she was just telling me that all these talks we were actually discussed the whole day today about it. So thanks a lot. That was quite well received. Plenty questions are posted. I just hand over the stage to Sebastian to chair the discussion session.
Okay.
Hi
Well,
from Susanna's part as well.
well, thank you very much, Anita, for a great and really interesting talk. And hello, Susanna. It's good to see you as well. And really nice to have that EU-wide collaboration here going on in the webinar today. So yes, Hardy said lots and lots of questions, and I'm trying to sort of go through them in a semi-logical way. And Willemijn starts saying, "Thank you, Anita, for the very interesting presentation." And she says, it is really encouraging to see that the Austrian society has accepted the new technology of underground hydrogen storage so well and fast. Do you think other countries would face the same easy societal acceptability towards underground hydrogen storage?
Um, yes, I think definitely we have a chance. It's how we bring it to the public. So I know that when we had this well in Leyen, also the first project, or we make sure that we involved a lot of the local people around them. That means during not just only for the opening ceremony reasons on the field, we had days that people could come and ask questions. So we also have there's they call it in Austria the long night of research. So people could lange Nacht der Forschung in German, and people would come and visit and ask questions. So it's very this open process and this transparency with people around there, and also not just a good contact with the mayor and to explain to them. And it's so well accepted in the region, and that's why that we did not have an issue to start with the underground sun storage 2030, which is another field, Rubensdorf, which is a slightly different area within Upper Austria, but another town council. Yeah.
So thank you much. I'm just going to ask a quick own question. Does it help that somewhere like there are regions in Austria where there's quite a bit of natural seasonal gas storage, underground gas storage already? Did that help to sort of engage with the society and remove some of the angst, the worries that the local citizens may have? That experience with gas storage help to ease concerns?
I can't. I don't really think so that the storage, because it's quite a very different area. So this and where our storages are, but we know that from our experience that always engaging as much as possible from the beginning on is good. And I can't really I can't compare because the storages that we have are very big facilities,
Hmm.
and the one in underground sun storage is a very small facility as well. So it's slightly a different worry or whatsoever. And with this renewable, definitely they're very the society is very welcoming.
Okay.
And I must say that few recently we also have from the state council from Kampen, they've shown interest if we would like to, if underground sun storage works, if we would actually also like to create kind of an energy autark thing within the small village. And that
Yeah.
is a very, very good feedback.
Definitely some interesting lessons to learn how to engage with society and put that positive aspects on there. You stay on the big picture for a little bit longer. So Mengji Zhao asks, "Hi Anita, thank you for your talk. Is underground hydrogen storage techno-economically justifiable?"
At the moment, I would say no, because to run my electrolysis unit, I need electricity. And where does my yeah, no, but this is one way. It's not feasible yet, but going in that direction to see, it's a proof of concept that we are looking at. And it is not feasible yet, I would say, techno economically.
Okay, thanks. Um,
Emphasize on yet.
yes, yeah, that's why I was faulting the emphasis on yet, and with what is happening to the energy market and the huge investments these days into renewable energy, which have, for the first time, I think last year, exceeded investments into the classical hydrocarbon
Mhm.
system, oil and gas industry. We will need this. We will need the storage, and as Hardy quite nicely says, the biggest batteries under our feet. So
Yeah,
for the storage,
I think we will
yeah,
also get used to paying more for
yeah,
the
yeah.
electricity, and then it makes everything very relative.
Yes, and on a day like, I don't know what the weather is in Austria or in Brussels, but it's very grey. There's not a lot of wind. There's a bit of wind in Delft, but probably these would be the days where we need
Hmm.
to balance demand from
Absolutely. Colleagues have
to good
flown from
storage.
Chicago to this event, Sebastian. It's snowing there. It's
Yeah.
we are
Yeah.
not the grayest part of the world even at this moment. So there are white regions actually at this moment. Yeah.
So we have another question from Willemijn and Herminio, so two PhD students and colleagues here at in Delft. So that relate to the surface facilities and making life easier. So Willemijn asked, my second question is about wells and infrastructure. Did you use special H2 approved well instruments and cements, or did you adapt the ones used for the gas industry? And
Um,
and Herminio just follows up because to what extent the infrastructure of depleted gas reservoir could be used for hydrogen storage? What would be the necessary adaptation? So
yeah.
again, making
Yeah.
things easy.
Yeah. These were slides that I didn't have for today's presentation, but definitely we have so we have adapted the current well bore that we use, but then we have changed and before we changed the tubings that we use gas tight tubings, and previously in the well we didn't have gas tight tubings. And the other one is we did a CBL and basically a CBL measurement to see that everything is intact. So I
Okay.
think that answers the question that we didn't use a special cement, but we checked the well integrity by
Yeah.
doing the ultrasonic measurements before. And that is also one of the from the how do I say the we have evaluation report. So when we get this yes, we can do such a storage, we have to show that yeah, we would do the CBL measurements and under ultrasound measurements before and at the end of the project. So we have to build out our tubings and again show that the integrity is still there.
Okay.
And yeah.
Great. Thank you. We have the questions, two questions are pretty much identical questions. So I'm going to one
Hmm.
from Isan Ranai and one from Said Harati. So I'm going to put Said's questions around up and she asks, how much cushion gas are you going to use or have used for storage? Have you done any analysis on the role of cushion gas, the type, the ratio, etc.? And Isan's question is very similar around the role of cushion gas.
um, yeah. In terms of definitely we have done, as in we wanted to have it's also on in terms of timing of the project and everything, but roughly we've decided that we wanted as cushion gas to be as much as hydrogen, so that during the extraction I don't have a lot of natural
Mm.
gas in my hydrogen because of my surface facilities. And we tried to balance it out to about 50%, 50, half half kind of, or one third natural gas and two thirds of the entire volume of cushion gas to be one third natural gas and two thirds hydrogen.
Thank you. Um, Giorgio Mio asks, how will the hydrogen be used after storage? Is it industrial processes, heating?
Um, we would in this project we would be using the hydrogen within our because within our whole system or of the natural gas system there in Upper Austria. So to heat up things around in the facilities that we have there. So we to use the energy internally.
Okay, that's really interesting. So not industrial, not large scale industrial
Not
processes then.
yet, because there are a few authority things that it doesn't then come under the yeah, because there are more regulations that are not
Mm.
clarified yet to put it into the grid and everything. So therefore we're using it for ourselves.
Okay,
Slightly being slightly self-sufficient, if I would put it the other way. Mhm.
good. Really interesting. Thank you. Um, Tejas asked, could you comment on the typical Reynolds number corresponding to hydrogen flow in the porous reservoir? How do you characterize flow as turbulent? You mentioned turbulent flow and the impact on dispersion.
Yes, turbulent in terms of when my I forgot now, I don't have it by heart, but when my Reynolds number is above this level, then it goes into turbulent flow, and I can't decipher to one point in a reservoir and say that I have turbulent flow here and I have laminar flow there, but we believe through the heterogeneity that I just don't have a highway, but I have some parts that have laminar flow and some parts where I have permeability strong changes. I do have a turbulent flow, and this is what that we are analyzing now in this project.
I'm sorry to interrupt. Is it more on the inertial forces are important, or it's really turbulent, which is Reynolds above 10 or so?
Yeah, above 10 or so
Yes.
Reynolds.
So you
That's
observe
what
that. Okay.
we think that must be.
There might
We
be.
think that it must be that because in terms of diffusion, we did not get. So it's basically, yeah, when I drop a droplet of ink into water, if I don't stir it, it just diffuses through. But I just have to stir a bit, and that already gives me a Reynolds number that it's high. Although it doesn't seem that it's so turbulent, but that is that idea that
I see.
we
At
are
the
trying.
porous scale, you're talking about the
Yeah.
grain scale dynamics. Oh, I see. Okay. Okay. Now clear. Okay.
Yeah. Yeah.
We have a few questions around reservoir integrity from our audience, and I start again. Firmino, and he says, I have a question. How did you perform the caprock integrity test for your pilot?
Yeah, it's a series of many things as that was explained in the slide. I thought that we did initially a caprock, so we took similar caprocks as we had and we tested it in laboratories was with dry gas and to see how the permeability looks like when I flush through methane and flush through hydrogen, and that was this order of magnitude that I showed that they were similar. And then as we got more, this was 10 years back, and then we thought, but the wet part, wet hydrogen is also important to know. And this is what now that we are looking at. When I expose to wet hydrogen, what changes my equilibrium in terms of my caprock? And for this, we are using some caprocks that we've gained from the drilling well from Leon for these laboratory experiments, pressurized to 150 bars and things like that. Yeah.
Thank you. And just so follow-up question on this. So, Yomio, this is very interesting talk. Are you waiting for the results from the lab on the caprock interaction, or will you start injection in March anyhow?
We would start injection, yeah, anyhow, because we do have results from the previous project. We would start the 100% in hydrogen in injection in March 2022 or April, depending on all our surface facilities. And parallelly, we have laboratory experiments that should come out sometime next year to confirm these. Yeah.
And so the last question related to the caprock integrity, Banda wonders, is there a possibility of microfracturing that could lead to enhanced permeability, or do you not expect to see this at all?
I don't expect to see this because from pressure transient analysis, if there, when my behavior seems the same over, we keep doing the pressure transient analysis over time, and we don't see that. And also this permeability increase, we see that with other storage operations as well, that through cycles of injection and withdrawal, that the permeability improves. Yeah, I can't say permeability improves because, yeah, but the wellbore performance improves.
Okay. I see there are a few more questions in the talk, in the chat, but I think you probably have answered them, most of them already. So I know that Hardy needs to run back as well to an important energy authority meeting. So I would like to thank the audience for some really excellent questions. Apologies if I haven't taken all your questions. Anita, thank you very, very much for a great and informative talk, for making the time to share your experience about really exciting, really important topic. And Hardy, over to you for some final closeout remarks.
Much. Yes, thanks a lot, Sebastian. Thank you very much, Anita, for this excellent talk. Plenty questions, and I would assume we could run it until midnight with many questions to come. I would like to take the chance to announce our next speaker for next month, December. We are going to host Anne-Marie Montendam Boss. She's my colleague for many years, but I wanted to pronounce her family name accurately. So Anne Marie Montedam Boss will be our next invited speaker. She will speak on 15th of December, right before the New Year vacation. So until next month, now we should say stay happy, healthy, and tuned into our channel for another geoscience and geoenergy webinar. And have a good weekend and all the best. And thank you very much once again, Anita, and all the audience for the great questions.
Thanks a lot.
Thank you, Anita. Thank you. Bye bye, everyone.
Bye bye.